All right, so continuing on with these problems, let's take a look at problem number 5. Under what situations is pH equal to pKa? This is something that I see people misapply a lot. Like we hear this trick, pH equals pKa, and we start trying to apply it to a lot of different scenarios. And this is only true in a very limited set of circumstances. So let's take a look at when this happens. So if you look at your Ka expression, it looks a little bit like this. It's, products over reactants. And let's say you have a point in which your concentrations of HA and A minus are equal. Let's say they're both 1 molar. Then what would happen mathematically, you'd have one on the top, one on the bottom. They would cancel out, and you'd be left with Ka equals H plus. If you take the negative log of both sides, you get pKa equals pH. So this is only true when you have equal amounts of HA and A minus. And when you have that, you have a specific kind of buffer. So this happens with buffers. Okay, so is pH equal to pKa when you have a pure weak acid? Nope. How about a pure strong acid? Nope. When you have titrated a weak acid to its half equivalence point? Yes. Okay. Let's scroll back to an earlier problem. This is exactly what's happening in problem number 3, part B. See, what we did in problem 3, part B, is I had some acid, and I used up half of it to make some base. So at this point, I have 50 acids and 50 bases. So notice right here, my concentration of my acid is equal to the concentration of my base. This happens when you are halfway to equivalence in a titration. Okay, so that happens in C. How about when you're at equivalence? Nope. When you're at equivalence, you have pure conjugate base. Let's actually draw a picture off to the side here. So if we are looking at a graph of pH as you are adding, volume of hydroxide, and this is your pH of your acid, initially it's going to start out low because you've got pure HA. Can you use pKa at this point? Nope. I'm going to go along and I'm going to titrate it. Okay. Over here at the end, you've got pure A minus. Right here in the middle is where your HA is equal to your A minus, because you're halfway there. So half of your original stuff is still in the solution, and you're halfway to making your A minus. So if you started out with 100 here, at the end you're going to have 100 A minuses, and right here in the middle you're going to have 50 of each. So you have a buffer, and at this point right here, this is where your pH is equal to pKa, and that's at this point only. Okay, so how about E? When you've combined equal amounts of weak acid and strong base, that's actually the same thing as D. That is the equivalence point. And how about F? Yep, when you've titrated weak base to its half equivalence, you have the same thing happening here. You're starting out here with a pure weak base. As you titrate it, you're going to turn that base into its conjugate acid. But when you're halfway there, you've got half base and you've got half acid. So you've got the combo right here. So again, if we start out with 100 bases here, at the end we'd end up with 100 acids, but in the middle you're going to have a 50-50 split. So right here in the middle, your pH is going to equal your pKa. It doesn't matter if you started with an acid or base. At the midpoint, you're still going to end up with equal amounts of acid and base, so your pH is going to be determined by your pKa. Okay, and this one isn't good, because at equivalence, this would be pure weak acid. So let's look a little bit more at buffers and how they work. So here's a buffer. We're making a buffer from acetic acid and sodium acetate. Okay, notice I have equal amounts of my weak acid and my conjugate base. This is my weak acid. This right here is the source of my anion, my conjugate base. It's this guy right here. It's 0.1 molar of each. So think about what we just said here. The pH is going to equal the pKa of the acid. Do this without a calculator. Let's estimate what the pKa is. So here's my Ka value. pKa is the log of this number. So the log of 10 to the minus 5 is going to be around 5. So the pH is going to be around 5-ish, a little bit less than that, probably like around 4-ish. So you want to be able to do that without your calculator on the multiple choice. So we want to think about how buffers work. So like, what makes a buffer a buffer? Why does it resist change in pH? How do buffers do that? Well, what happens when we add acid? Let's say we come along and we dump some acid into your container. My container has HC2H3O2 in it, and it's got some C3H2O2 minus ions. Well, is the hydrogen interested in sticking to anybody? Sure, we've got an anion right here that's a weak base, so it's going to come along and it is going to stick with my acetate ion, making HC2H3O2. So when you add HCl to your buffer, it's going to decrease the concentration of your anion, the conjugate base, and increase the concentration of your acid. I'll just use my general symbols there. When you add hydroxide, the opposite thing happens. The hydroxide is going to react with the acid component of your mixture, generating the conjugate base and water. So it's going to decrease the concentration of HA and increase the concentration of A minus. And why does the buffer resist change in pH? Because one way of phrasing it is the stuff in the buffer is able to use up or react any H plus or OH minus that you add. And it's those freely floating H pluses and OH minuses that affect the pH. So if you can remove those from the solution, then your pH is not going to change by very much. So that is how buffers work.